And so to gear up for our next part, couldn't we say that this right here, this plane, z equals 4x minus 2y minus plus 2y minus 3, that's a good approximation of our f of xy equals 2x squared plus y squared. But only if what? Only if we're near this point. So only if xy is near 1, 1. Okay? And so what we might say is this, f of xy is approximately equal to 4x minus plus 2y minus 3. Which is not a whole lot easier than 2x squared plus y squared, but it is linear, right? Instead of squaring. And so if you get more complicated functions of x and y, this still gives you a nice approximation, near a particular point. And and this is one thing they'll have us do is approximate f of 1.1 0.92 using this linear approximation, because that point 1, 1, 0.92 is near 1, 1, isn't it? It's close to 1 and it's close to 1 there. So the x and y are pretty close there. And so instead of having to plug that in, 2x squared plus y squared, and get that value, we can just do it here, right? We can do 4 times 1.1 plus 2 times 0.92 minus 3, which I think gives me, what does that give me? Okay. Yeah, I did it different. Okay. So it's 4.4 plus what, 1.84. 3.24. Okay. What's the actual value of f of 1.1, 0.92? Well, the actual value would be 2 times 1.1 squared plus 0.92 squared. 2 times 1.1 squared. Oh, 3.2664. That, yeah. And so, yeah, that does give me pretty close rendition. Only off by a few hundredths. Okay. Which is pretty close. Pretty close. Okay. All right, and so that's one thing that they point out then is that also analogous to something we did in 2 dimensions, where we talked about linear approximations and linearizations. We can use this this tangent plane at a particular point to come up with a linearization. It's really the same, very same idea, very same. For function f of xy, the linearization of f at the point a, b, f of a, b. Okay, that's just using a little different notation. Instead of x, y, and z, they're using a, b, and then z is the f value at ab. All right. Is L of xy, we called it in 2 dimensions, we just said L of x. But now the linearization L of xy is, well, it's going to be f of ab plus f partial derivative of f with respect to x at ab times x minus a plus the partial derivative of y at ab times y minus b. Okay? Now please note, this is nothing really that new or different, because this just comes from, remember we had our tangent plane, z minus z0 equals partial with respect to x of x0, y0. Let me write it all out here just to make the comparison. Partial of y of f, partial derivative of f at y, or of y, with respect to y, x0, y0, times y minus y0. Okay, just a lot to write there. But this is the same thing, isn't it? This is the same exact thing, because where does this come from? That's your z value at your point. So that's over here. So what did they do? They just add it to the other side. Okay? So we just move that over, z0 plus blah, blah, blah. The same thing we got. And instead of x0, y0, they're calling it a and b for the x0 and the y0. It's the same thing. Okay. All right. So now the other part then to this is the linear approximation then, which we kind of did, but the linear approximation of f at a is this. F of xy is approximately equal to f of ab plus f of x of ab times x minus a plus f partial y ab y minus b. Okay? So this again is just pointing out that we can approximate function values using this linear approximation or linearization. Those are going to be, as long as you don't get too far out, as long as your x and y are near, okay, the approximations are better. If your xy is near AB, right? If AB is 1, 1, and you try to do the approximation at -5, 7, that's probably not going to be too good, right? If AB is 1, 1, like we just did. That's not going to be too good of an approximation. But as long as xy is near AB, then this result right here, this linearization, is going to give you an approximation. Pretty good approximation. All right, so let's do another one here, just using this terminology then. Okay, find the linearization of f of xy equals x squared y cubed times y cubed at, we'll just use 1, 1, 1, okay. And then use that to approximate f of 0.9, 0.9. Just a little bit down from that, if you will. Okay, so linearization, we know that's L of xy equals f of AB plus partial of f with respect to x at AB times x minus a plus the partial of f with respect to y at AB, y minus b. Which in this case we've got a and b are 1 and 1. This is the a, this is the b. And nicely this would be function value at AB. So we've got all 1s there. So we know this is 1, a is 1, b is 1. The only thing we need to come up with is the partial of f with respect to x and the partial of f with respect to y. So the partial, what would the partial of f with respect to x be? Well, again, the y is a constant, so we're just doing get rid of the x, so it would be 2x y cubed, wouldn't it? And then the partial of y would be same thing, except the x is constant, so it would be 3y squared times x squared, 3x squared y squared. All right. And so the a and the b are 1, so our f of x at AB is just going to be 2 times 1 times 1, which is 2, and the f of y at our particular AB 1, 1 is going to be 3 times 1 squared times 1 squared, so that's just going to be 3. So our linearization would be 3xy, L of xy equals, you said this is 1, this is 2, the a is 1, so bx minus 1. The partial of f with respect to y is 3, so that would be 3 times y, and the b is also 1, so we get that. If we didn't want the parentheses, I guess, we can go ahead and see, that would be 1 plus 2x minus 2 plus 3y minus 3, so that would be 2x plus 3y minus 4. I believe. Does that sound right? Didn't have that one worked out. Okay. I think that's right. All right, so the second part was use that approximation, linearization, to approximate f of 0.9, 0.9. And so that would be approximated by this then expression. So f of 0.9 is going to be approximately 2 times 0.9 plus 3 times 0.9 minus 4. That's 1.8 plus 2.7 minus 4. And so that is 4.5 minus 4. 0.5. 0.5. Okay. Now, what's the actual value? What's the actual? I don't have time to do it. The 0.9 squared times 0.9 cubed, yeah, which is a lot harder to do by hand, but calculator can handle that. 0.81 times 0.027? .590. Yeah. Yeah. All right. So pretty close. Pretty close. All right.